The world of classical physics, which governed much of the scientific understanding for centuries, was based on the fundamental assumption that the laws of nature are predictable, deterministic, and absolute. Every event or process in nature, according to classical physics, could be described with certainty and accuracy based on its initial conditions. If we knew the present state of a system, we could predict the future behavior of that system with flawless precision. This belief was a cornerstone of physics, giving rise to the laws of motion by Sir Isaac Newton and the foundational principles of mechanics, electricity, and magnetism. However, in the early 20th century, a revolutionary discovery would shatter the very foundation of certainty upon which classical physics rested. This discovery came in the form of quantum mechanics, and at the heart of this new theory was a concept that defied all intuitive understanding uncertainty. The discovery of quantum mechanics marked the beginning of the end for the certainty that had long governed the physical sciences. The breakthrough that led to this paradigm shift came from the work of German physicist Max Planck. In 1900, Planck was investigating the phenomenon of black-body radiation, a problem that had puzzled scientists for years. Classical physics could not explain why hot objects emitted radiation in certain patterns of energy, nor could it predict the spectral distribution of this radiation at different temperatures. Planck, while trying to solve this issue, proposed that energy could not be emitted or absorbed continuously, as classical theory suggested. Instead, energy existed in discrete packets, or quanta. This idea of quantized energy was a drastic departure from the smooth, continuous behavior expected by classical physics. Planck's theory, known as Planck's law, initially seemed like a mathematical trick away to fit observed experimental data. However, this seemingly small shift in understanding had profound implications. It laid the groundwork for the emerging field of quantum mechanics, which would forever alter the way we understood the nature of reality. Around the same time, Albert Einstein extended Planck's ideas to explain the photoelectric effect, another unresolved issue in physics. In 1905, Einstein proposed that light, traditionally thought to be a continuous wave, could also be described as a stream of discrete particles, later known as photons. This dual nature of light, both wave-like and particle-like, was a startling revelation. It was a radical departure from the established belief that light was purely a wave, as described by James Clerk Maxwell's electromagnetic theory. Einstein's theory of light, quanta, further disrupted the classical understanding of the universe. The breakthrough was not limited to light energy alone. In 1913, Niels Bohr introduced his model of the atom, which was another crucial step toward the quantum revolution. Bohr proposed that electrons in an atom could only occupy specific orbits, and they could not exist in between these orbits. The idea that electrons could exist in discrete energy levels contradicted the smooth continuum expected by classical physics. Bohr's work brought the concept of quantization into the realm of atomic structure and set the stage for further developments in quantum mechanics. As more experiments were conducted, the implications of quantum theory became increasingly apparent. In 1927, Werner Heisenberg formalized one of the most unsettling consequences of quantum mechanics, the uncertainty principle. According to Heisenberg, the more precisely we measure one property of a particle, such as its position, the less precisely we can know its momentum, and vice versa. This principle destroyed the long-held belief in determinism. The notion that we could know both the position and momentum of a particle simultaneously with absolute certainty was now proven to be impossible. In fact, uncertainty was not just a limitation of our measurement tools, it was a fundamental property of the universe. Heisenberg's uncertainty principle had profound philosophical implications. It suggested that at the quantum level, the universe was not governed by the neat, orderly, predictable laws of classical physics. Instead, the behavior of particles was governed by probabilities. This notion of probability was codified by the Schrödinger equation developed by Erwin Schrödinger in 1926. Schrödinger's equation provided a mathematical framework to calculate the probability of a particle's position and momentum, rather than their exact values. This shift from certainty to probability meant that the future behavior of quantum systems could only be predicted in terms of likelihood, not with the absolute precision once believed to be possible. The realization that uncertainty and probability were intrinsic to the fabric of the universe was a profound shock. It not only shattered the certainty of classical physics, but also forced scientists to reconsider the nature of reality itself. Was the universe truly deterministic, as Newton had proposed, or was it inherently uncertain, as quantum mechanics suggested? For the first time, scientists were faced with the unsettling possibility that the universe did not behave with the rigid predictability they had always assumed. The implications of quantum mechanics were not limited to the world of subatomic particles. They extended into the realms of philosophy, epistemology, and even metaphysics. If the universe was fundamentally uncertain, what did that mean for the concept of free will, the nature of consciousness, and the very meaning of knowledge itself? These were questions that had never been considered within the context of classical physics, but now they were unavoidable. For many, the discoveries of quantum mechanics not only destroyed certainty in physics, but also opened up new, uncharted territories in the understanding of the universe. As the 20th century progressed, the development of quantum theory continued to unfold with contributions from physicists such as Louis de Broglie, Paul Dirac, and Richard Feynman. Each new development seemed to reinforce the idea that the universe was not a deterministic machine, as had been previously believed. Instead, it was a place where probability, uncertainty, and indeterminacy were fundamental characteristics of nature. Today, quantum mechanics is not just a branch of physics, it is the very foundation of much of modern technology. From computers to lasers to medical imaging devices, the discovery that shattered certainty in physics has become the cornerstone of our technological world. Yet, despite its success in explaining the microscopic world, quantum mechanics continues to challenge our understanding of reality. The very fact that we can use quantum mechanics to build technologies that work does not mean that we fully comprehend the nature of the universe it describes. The journey from the certainties of classical physics to the uncertainties of quantum mechanics has been one of the most profound intellectual revolutions in human history. It has forever altered the way we view the world, forcing us to accept that uncertainty is not an anomaly or an error in measurement, it is an inherent feature of the universe. The physics discovery that destroyed certainty in the early 20th century reshaped not only science, but also the way we perceive the nature of reality itself. As quantum mechanics continued to unfold, the full magnitude of its implication for our understanding of the universe became increasingly clear. One of the most profound shifts that came with the advent of quantum theory was its challenge to the classical view of physical reality. Classical physics had long relied on the belief that the universe operated according to rigid, deterministic laws. In this view, if we knew the position and velocity of every particle in the universe, we could theoretically predict the future with perfect precision. This was the essence of Newtonian mechanics, the idea that the universe followed a predictable, clockwork-like system, governed by deterministic laws. However, with the rise of quantum mechanics, this worldview was radically altered. In 1927, Heisenberg's uncertainty principle challenged the very foundation of classical physics. The uncertainty principle argued that there were limits to how precisely we could know certain properties of particles, specifically their position and momentum at the same time. This was a direct contradiction to the deterministic framework of classical physics, where it was assumed that the universe could be fully described by the positions and velocities of particles at any given time. Heisenberg's principle was not merely a limitation of measurement technology or an inherent flaw in our instruments, it was a fundamental feature of nature itself. The idea that there were intrinsic limits to our knowledge of the physical world was a startling revelation. It meant that, at the most basic level, the universe was not predictable with absolute certainty. The behavior of particles could only be described probabilistically, meaning that the future of any given system could only be known in terms of likelihoods, not absolutes. In addition to the uncertainty principle, the development of wave-particle duality further undermined classical ideas of certainty. The wave-particle duality, first proposed by Louis de Broglie and later confirmed by experiments such as the double-slit experiment, suggested that particles such as electrons could behave both as particles and as waves, depending on how they were observed. This was a direct challenge to the classical view that particles had fixed properties, such as location and velocity. Instead, quantum mechanics introduced the concept of superposition, the idea that particles could exist in multiple states at once, only choosing a particular state when measured. This strange and counterintuitive behavior of quantum particles was best exemplified in Schrödinger's famous thought experiment, which introduced the concept of the quantum superposition in the context of a cat that was simultaneously both alive and dead until observed. This paradox highlighted the bizarre and unsettling nature of quantum mechanics, where the act of observation itself appeared to play a central role in determining the state of a system. The very notion that particles could exist in multiple states simultaneously and that their state could depend on the act of observation seemed to defy all conventional understanding of the physical world. The concept of quantum entanglement further added to the complexity and mystery of quantum mechanics, proposed by Einstein, Podolsky, and Rosen in 1935 and later explored in more detail by physicists such as John Bell. Entanglement refers to a phenomenon where two particles can become correlated in such a way that the state of one particle is instantly linked to the state of the other, no matter how far apart they are. This non-local behavior contradicted the idea that information could only travel at the speed of light and raised questions about the nature of space, time, and causality. Entanglement seemed to suggest that particles could be interconnected in ways that transcended the conventional understanding of distance and time, further dismantling the classical view of a predictable, causally determined universe. The challenge that quantum mechanics posed to classical physics was not limited to the realm of subatomic particles. It extended to the very nature of reality itself. If the behavior of individual particles was governed by probabilities rather than certainty, then what did this mean for our understanding of the macroscopic world? Was the universe itself subject to inherent uncertainty? Or was it only the microscopic world that was governed by quantum rules? As the 20th century progressed, physicists began to realize that quantum mechanics was not simply a set of abstract principles that applied only to the microscopic world. Its effects had real-world implications, and technologies that relied on quantum principles, such as semiconductors and lasers, began to shape the world in unprecedented ways. The very technologies that were built on the principles of quantum mechanics showed that, despite the strange and counterintuitive nature of the theory, it was an essential part of understanding and manipulating the physical world. At the same time, the philosophical implications of quantum mechanics became more apparent. The question of whether the universe was deterministic or probabilistic had a profound implication for our understanding of free will, causality, and the nature of reality. If the universe was fundamentally uncertain, then what did that mean for human agency and choice? Was our understanding of causality, where one event leads directly to another, still valid in a world governed by probability? These were deep and unsettling questions that quantum mechanics raised but did not fully answer. The philosophical debates surrounding quantum mechanics were further complicated by the advent of the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg. The Copenhagen interpretation posited that the wave function, which described the probability of finding a particle in a given state, collapsed into a definite state when measured. This interpretation suggested that reality was not fully determined until it was observed, further challenging the classical idea of an objective, independent reality that existed outside of our observation. In contrast, other interpretations, such as the many worlds interpretation proposed by Hugh Everett, suggested that all possible outcomes of a quantum event actually occur, but in different parallel realities. According to this interpretation, every measurement of a quantum system results in a branching of the universe into multiple, parallel worlds, each corresponding to a different outcome. This interpretation presented an even more radical view of reality, where the very notion of a single, objective universe was replaced by a multiverse of parallel realities. The discovery that the physical world was governed by uncertainty and probability was a deeply unsettling revelation, not just for physicists, but for the entire human experience. The idea that we could no longer rely on the laws of nature to provide us with absolute certainty about the future changed our relationship with the world around us. The idea that reality was not a fixed, predictable machine but a realm of probabilities and uncertainty, forced us to confront the limits of our knowledge and the limitations of human perception. It raised questions not only about the nature of the universe but about our place within it. Quantum mechanics has since become the foundation of modern physics, and its applications are essential in everything from computing to telecommunications to medicine. Despite its incredible success in explaining the behavior of the microscopic world, quantum mechanics continues to challenge our understanding of reality. The discoveries that began with Planck and Einstein in the early 20th century have transformed not just the field of physics, but also the very way we view the universe. The physics discovery that destroyed certainty has led to a deeper, more nuanced understanding of the nature of reality, one that embraces the unpredictable, the uncertain, and the probabilistic. Yet, despite the successes of quantum mechanics, it remains a mystery in many ways. Its implications for our understanding of the nature of reality and the limits of human knowledge continue to provoke debate among scientists, philosophers, and thinkers alike. The question of whether the universe is truly probabilistic or whether there is an underlying hidden determinism that governs all of reality remains one of the most profound questions in science. As we continue to explore the depths of quantum theory, one thing remains certain: the physics discovered that destroyed certainty has forever changed the way we understand the universe and our place within it. It has shown us that the world is not as simple or predictable as we once believed, and that uncertainty, rather than certainty, may be the most fundamental characteristic of the cosmos. Quantum mechanics and the radical departure from certainty did not just affect our understanding of physical phenomena at the subatomic level, but it also transformed our perception of reality itself. One of the most revolutionary concepts introduced by quantum theory was the notion of superposition. Superposition, a direct consequence of wave-particle duality, proposed that quantum objects could exist in multiple states simultaneously until observed. This strange behavior, observed in experiments such as the double-slit experiment, completely shattered the classical idea of particles having well-defined positions and velocities at any given time. In classical mechanics, if a ball were to roll across a table, its position could be precisely known at any point in time. The ball's trajectory would be determined by its velocity and the forces acting on it. This intuitive picture of the world, where objects had fixed positions and followed predictable paths, had been ingrained in human thinking for centuries. However, quantum mechanics exposed this certainty as an illusion. In the double-slit experiment, when light or particles such as electrons were directed through two slits in a barrier, they produced an interference pattern on a detection screen behind the slits, suggesting that each particle was behaving as a wave, simultaneously passing through both slits at once. However, when a detector was placed to observe which slit the particle went through, the interference pattern disappeared, and the particles behaved as discrete particles, going through one slit at a time. This outcome was shocking. It suggested that the act of observation itself influenced the behavior of the particles, and until observed, the particles existed in a state of superposition, existing in multiple states simultaneously. This phenomenon of superposition extended beyond simple particles to complex systems as well. The concept of entanglement, introduced by Albert Einstein and his colleagues in the 1930s, further amplified the confusion surrounding quantum mechanics. Entanglement occurs when two quantum particles become so deeply linked that the state of one particle is directly tied to the state of another, regardless of the distance between them. If one particle is measured, the state of the other particle is instantaneously determined, even if it is light years away. This seemingly instantaneous transfer of information contradicted the principles of relativity, which stated that information could only travel at the speed of light. Entanglement not only undermined the classical notion of local realism, where objects have well-defined properties that are independent of observation, but it also suggested that the universe could not be fully described by classical physics. The bizarre nature of quantum mechanics became apparent in the famous EPR paradox, where Einstein, Podolsky, and Rosen proposed that quantum mechanics was incomplete because it implied spooky action at a distance, something that contradicted the principle of locality in physics. They argued that there must be hidden variables, undiscovered factors that could account for the strange correlations observed in quantum systems. However, over time, Experiments such as those conducted by physicist John Bell in the 1960s showed that the predictions of quantum mechanics were correct, and that no hidden variables existed that could explain the entanglement phenomena. Bell's theorem, as it became known, showed that quantum mechanics was not just a temporary scientific curiosity, but was in fact a new way of understanding the universe that could not be explained using classical concepts. The idea of superposition and entanglement forced scientists to grapple with the question of what it meant for an object or particle to have a definite state. Before quantum mechanics, it was assumed that a particle, even if it was not being observed, still had definite properties that could be known. But with the advent of quantum theory, this assumption was upended. Quantum objects were now described by a wave function, which provided the probability of finding a particle in a particular state, rather than a definitive answer. The wave function collapsed when the particle was observed, and its properties became well defined only at that moment. This probabilistic nature of quantum mechanics was not just a limitation of measurement techniques, it was a fundamental characteristic of nature itself. Unlike classical physics, where the future could be predicted with absolute certainty, given enough information, quantum mechanics provided only probabilities. This inherent uncertainty in the behavior of quantum systems was encapsulated by the Schrödinger equation, which governed the evolution of the wave function over time. However, even the Schrödinger equation, despite its predictive power, did not provide certainty about the behavior of individual particles. It only gave the likelihood of finding a particle in a given state. The philosophical implications of these discoveries were profound. If the universe at its most fundamental level was governed by probability and uncertainties, what did that mean for human experience? What happened to the classical notion of causality, where every effect had a direct cause? What happened to the idea that the universe was a deterministic system, operating according to fixed laws? The implications were far-reaching and went beyond just the realm of physics. Quantum mechanics suggested that at the core of reality, there was no inherent certainty. This realization raised questions about free will, the nature of consciousness, and the role of observation in shaping reality. Could the act of observing a system truly influence its state, as quantum mechanics suggested? And if the universe was governed by probabilities, did that mean that the future was inherently uncertain, and that the notion of free will was an illusion? These were questions that quantum mechanics posed, but did not answer definitively. For many, the philosophical implications of quantum theory were unsettling. The deterministic universe, with its clear cause and effect relationships, was replaced by a universe where the future could only be described in terms of likelihoods. The concept of certainty, which had been central to the classical worldview, was no longer tenable. Instead, uncertainty became the new foundation of scientific understanding. Despite the unsettling nature of these revelations, quantum mechanics has proved to be incredibly successful in explaining a wide range of phenomena, from the behavior of subatomic particles to the workings of semiconductors and lasers. Quantum theory has become the cornerstone of modern technology. It has allowed us to build technologies that rely on the principles of quantum mechanics, such as computers, GPS systems, and medical imaging devices. The success of quantum theory in the practical world has cemented its place as one of the most powerful scientific theories ever developed. Yet, despite its practical success, quantum mechanics continues to challenge our understanding of the universe. The questions raised by quantum theory about the nature of reality, the role of observation, and the meaning of probability are far from resolved. The discovery that the universe is not deterministic but probabilistic has forever changed the way we think about the world. It has shown that, at the most fundamental level, the universe is not a predictable, deterministic system, but a place where uncertainty reigns. The physics discovery that destroyed certainty has forced us to reconsider not just the nature of the universe, but also our place within it. As physicists continue to explore the implications of quantum mechanics, one thing remains clear: the universe is far stranger and more mysterious than we ever imagined. The discovery of quantum theory has shattered the classical understanding of certainty and has led to a new era of scientific exploration, one that embraces the uncertainty at the heart of reality and challenges us to rethink the very nature of existence. The realization that quantum mechanics undermines the certainty long held by classical physics has had profound effect, not only on the scientific community but also on the broader cultural and philosophical understanding of the universe. As we delve deeper into quantum mechanics and its implications, it becomes clear that the discovery of uncertainty has changed the way we perceive our reality. While the probabilistic nature of quantum mechanics opened up new avenues for scientific research, it also forced a reconsideration of long-standing assumptions in other fields, including philosophy, metaphysics, and even the concept of consciousness. Quantum mechanics brought to light the idea that the universe at its most fundamental level is not deterministic. Instead, it operates in a realm of probabilities where events do not follow a predictable path but are instead governed by likelihoods. This notion of an inherently probabilistic universe was a far cry from the certainty of classical mechanics, where, if all variables were known, the future could be predicted with precision. This shift had dramatic consequences for the way scientists approached the world, leading to the development of new theories, debates, and interpretations of quantum mechanics. One of the most significant areas affected by this discovery was the concept of causality, the idea that every effect has a cause. In classical physics, this notion was fundamental. Newtonian mechanics, for instance, relied on the premise that forces acted on objects in a predictable manner, with well-defined causes leading to specific effects. But in the quantum realm, causality was not as clear-cut. Quantum particles did not follow predictable, linear paths. Instead, their behavior was described by a wave function representing the probability of finding a particle in a given state at a particular time. This probabilistic behavior made it impossible to say with certainty what the outcome of a quantum event would be, even if the conditions were known. This departure from determinism forced physicists to reconsider the very nature of reality. In a world governed by probabilities, the concept of an objective reality, one that exists independently of observation, came into question. Before quantum mechanics, the idea that objects had intrinsic properties, such as position and velocity, was taken for granted. These properties were assumed to exist whether or not they were observed. However, quantum mechanics shattered this assumption. According to the Copenhagen interpretation, proposed by Niels Bohr and Werner Heisenberg, the properties of quantum systems are not definite until they are observed. Until that moment, particles exist in a superposition of all possible states, and only upon measurement do they collapse into one specific state. This led to the famous thought experiment known as Schrödinger's cat, which illustrated the paradoxical nature of quantum mechanics. In this experiment, a cat inside a box is simultaneously both alive and dead, as its fate is linked to the decay of a radioactive atom. Until the box is opened and the cat is observed, the cat exists in a superposition of both states. This was an unsettling realization. If quantum systems only have definite property when observed, then reality itself seemed to depend on the act of observation. The idea that the act of measurement could influence the state of a system challenged the classical notion of an objective, observer-independent reality. As physicists continued to grapple with these strange revelations, another concept emerged that further undermined the certainty of classical physics: quantum entanglement. This phenomenon, which was proposed by Einstein, Podolsky, and Rosen in 1935, refers to the situation where two particles become linked in such a way that the state of one particle is instantaneously connected to the state of the other, no matter the distance between them. When one particle is measured, the state of the other particle is immediately determined. This phenomenon, sometimes referred to as spooky action at a distance, appeared to defy the principle of relativity, which stated that information could not travel faster than the speed of light. The discovery of quantum entanglement posed another challenge to the classical understanding of the universe. Classical physics assumed that particles and objects were local, meaning they existed in a specific place at a specific time, and their properties were independent of other objects. However, quantum entanglement showed that particles could be non-local, meaning their properties were not confined to a single location. This idea of non-locality was not just a theoretical concept, but was experimentally verified in the 1960s through experiments based on Bell's theorem. These experiments showed that the correlations between entangled particles could not be explained by classical physics. further confirming that quantum mechanics was correct in its prediction of non-local behavior. As quantum mechanics continued to evolve, it became clear that it was not just a theory for explaining the behavior of subatomic particles, but a framework that could explain phenomena on a larger scale. The probabilistic nature of quantum mechanics, for example, was responsible for the behavior of semiconductors and the functioning of modern electronics, including transistors and computer chips. The discoveries that had undermined certainty in physics had, paradoxically, become the foundation for technologies that have revolutionized the world. Quantum theory also played a crucial role in the development of lasers, GPS systems, and medical imaging technologies, all of which rely on quantum principles to function. Despite its success in practical applications, quantum mechanics has continued to provoke debate and curiosity among scientists and philosophers alike. The philosophical implications of quantum mechanics remain unresolved to this day. If the universe is governed by probability and uncertainty, then what does that mean for the concept of free will? What happens to our understanding of time and space when the fabric of reality is shown to be uncertain at its core? These are questions that quantum mechanics continues to raise without providing clear answers. One of the most debated aspects of quantum theory is the interpretation of the wave function, the mathematical description of a quantum system. Different interpretations of quantum mechanics offer differing views on the nature of the wave function and its role in determining reality. The Copenhagen interpretation suggests that the wave function represents a probability distribution, and the act of measurement causes the wave function to collapse into a definite state. However, the many-worlds interpretation, proposed by Hugh Everett in 1957, suggests that all possible outcomes of a quantum event occur, but in separate, parallel universes. In this view, there is no collapse of the wave function. Instead, the universe branches into different realities, with each outcome being realized in a separate world. While the Copenhagen interpretation has been the most widely accepted, the many-worlds interpretation has gained traction in recent years due to its elegant simplicity and its ability to avoid some of the paradoxes associated with measurement. However, the many-worlds interpretation raises its own set of questions. If all possible outcomes occur, does that mean that every action we take is mirrored in an alternate reality? And if so, what does that say about the nature of our choices and the concept of free will? These are questions that quantum mechanics, despite its practical successes, has not yet answered definitively. The introduction of quantum mechanics, with its inherent uncertainty and probabilistic nature, has reshaped not just physics, but also our understanding of reality. It has shattered the certainty that was long associated with classical physics, replacing it with a world where probability and uncertainty reign. This shift has forced us to reconsider the very foundations of science, philosophy, and our place in the universe. As quantum mechanics continues to evolve, it promises to unlock even more mysteries of the cosmos, revealing a universe that is far stranger and more complex than we ever imagined. In conclusion, the physics discovery that destroyed certainty in the early 20th century has had far-reaching consequences, both within the realm of science and beyond. The advent of quantum mechanics has reshaped the way we think about the universe, forcing us to embrace uncertainty and probability as fundamental features of nature. It has challenged long-held assumptions about reality, causality, and free will, and its implications continue to reverberate across fields, ranging from technology to philosophy. Quantum mechanics has revealed that the universe is not a predictable, deterministic machine, but a place of possibility, mystery, and ultimately wonder. The uncertainty that it introduced into physics has become a cornerstone of modern science, driving new discoveries and shaping the future of human understanding. The emergence of quantum mechanics marked one of the most radical shifts in the history of science. It not only challenged the classical view of physics, but also upended the very foundations of our understanding of nature. Where classical physics had offered a universe governed by predictable laws, quantum mechanics introduced the idea that at the subatomic level, certainty no longer reigned. Among the most important contributions to this discovery was the development of quantum field theory, and the concept of wave-particle duality. These ideas led to a new paradigm in physics, one that forced scientists to reconsider everything they knew about the behavior of matter and energy. One of the key principles that emerged from quantum mechanics was the idea of wave-particle duality. In classical physics, light and matter were understood in strictly separate terms. Light was a wave, and particles, such as electrons, were discrete objects with well-defined properties. However, in the early 20th century, experiments such as the double-slit experiment revealed that this distinction was not as clear-cut as once thought. In the double-slit experiment, light, when passed through two slits, produced an interference pattern on a screen behind the slits, much like a wave would. But when the same experiment was performed with particles like electrons, a similar interference pattern was observed, suggesting that electrons, traditionally considered to be particles, also behaved as waves. This wave-particle duality of light and matter was one of the most striking discoveries of quantum mechanics. It suggested that at the most fundamental level, matter and energy could exhibit properties of both particles and waves, depending on how they were observed. This idea completely shattered the classical understanding of light and matter, and forced scientists to adopt a new, more nuanced view of the universe. According to quantum mechanics, particles like electrons could exist in a superposition of states, acting as both particles and waves until measured. This realization was a profound departure from the classical view, where objects were assumed to have fixed properties regardless of observation. The development of quantum field theory further extended this understanding, providing a more complete framework for understanding the behavior of particles and fields. Quantum field theory is based on the idea that fields, rather than particles, are the fundamental entities in the universe. These fields permeate all of space and can exist in a variety of states, including excited states that correspond to particles. According to this theory, particles are simply excitations or disturbances in these fields. The theory offers a way of understanding how particles interact with one another, as well as how forces, such as electromagnetism and gravity, arise from the interactions between fields. One of the most important concepts in quantum field theory is the idea of virtual particles. Virtual particles are temporary particles that spontaneously appear and disappear within quantum fields. These particles are not directly observable but can influence the behavior of real particles. For example, in the case of electromagnetism, virtual photons are exchanged between charged particles, mediating the force of attraction or repulsion between them. The concept of virtual particles was a key insight of quantum field theory, helping to explain the forces of nature in a way that classical physics could not. As quantum mechanics progressed, it became clear that its principles extended beyond just the behavior of individual particles. The field of quantum electrodynamics, QED, developed by Richard Feynman, John Ward, and Julian Schwinger in the mid-20th century, demonstrated how quantum mechanics could be used to describe the interactions of light and matter in a unified framework. QED provided an explanation for phenomena like the scattering of light by electrons and the creation and annihilation of particles. Through its use of Feynman diagrams, graphical representations of particle interactions, QED allowed scientists to calculate the probability of various interactions occurring, providing a more accurate picture of the interactions between matter and energy than classical physics had ever been able to. The development of quantum mechanics also led to a shift in our understanding of energy itself. In classical physics, energy was considered a continuous quantity that could take on any value. However, in quantum mechanics, energy was found to be quantized, existing in discrete levels rather than being continuous. This idea was first proposed by Max Planck in 1900 when he introduced the concept of energy quanta to explain blackbody radiation. Planck's theory suggested that energy could only be emitted or absorbed in specific, discrete amounts rather than a smooth, continuous flow. This concept laid the foundation for the later development of quantum mechanics and was fundamental to the discovery of wave-particle duality. The quantization of energy also had profound implications for the structure of atoms. In the early 20th century, Niels Bohr developed a model of the atom in which electrons orbited the nucleus in specific, quantized energy levels. Electrons could not exist in between these levels, but they could absorb or emit discrete amounts of energy when they transitioned from one level to another. This concept of quantized energy levels was revolutionary, as it explained the discrete spectral lines observed in the light emitted by atoms. Bohr's model was a key step in the development of quantum theory and provided important insights into the structure of matter. However, the true power of quantum mechanics was not realized until the 1920s, when physicists such as Werner Heisenberg, Erwin Schrödinger, and Paul Dirac developed the mathematical tools that allow for a more comprehensive understanding of quantum phenomena. Heisenberg's uncertainty principle, which stated that the position and momentum of a particle could not both be precisely known at the same time, introduced a fundamental limit to the accuracy of our knowledge of quantum systems. Schrödinger's wave equation, which described the behavior of quantum particles as waves, provided a mathematical framework for calculating the probability of finding a particle in a given state. These discoveries ultimately led to the realization that the universe at the quantum level does not operate according to the deterministic laws of classical physics. Instead, particles exist in a state of probability, with their position and velocity only defined in terms of likelihoods. The idea of a deterministic universe, where every event follows logically from previous events, was replaced by a probabilistic view of reality, where the future of a system could only be predicted in terms of probability. One of the most striking features of quantum mechanics is the concept of wave function collapse. According to quantum theory, particles exist in a superposition of states, each with its own probability. When a measurement is made, the wave function collapses, and the particle assumes a definite state. This collapse of the wave function was one of the most puzzling aspects of quantum mechanics, as it suggested that the act of observation itself influenced the state of a quantum system. This idea of an observer-dependent reality was deeply unsettling, as it implied that the universe did not exist independently of our perception of it. The philosophical implications of wave function collapse and the probabilistic nature of quantum mechanics were profound. If the universe at the quantum level was governed by uncertainty and probability, then what did that mean for the nature of reality itself? Could it be that our perception of the world was an illusion, and that the universe existed only as a set of probabilities until we observed it? These questions raised fundamental challenges to our understanding of the relationship between the observer and the observed, and they continue to provoke debate and discussion in the philosophy of science. Despite these philosophical challenges, quantum mechanics has proven to be an extraordinarily successful theory. It has been confirmed through countless experiments and has provided the basis for technologies that have transformed the modern world. From semiconductors and lasers to medical imaging and quantum computers, the practical applications of quantum mechanics are vast and far-reaching. The discovery of quantum mechanics may have destroyed the certainty that was once the foundation of classical physics, but it has also opened up new realms of scientific inquiry and technological advancement. The development of quantum field theory, wave-particle duality, and the quantization of energy marked a new chapter in the history of physics, one that continues to shape our understanding of the universe. These discoveries forced scientists to abandon the certainty of classical mechanics and embrace a new, probabilistic view of reality. The impact of quantum mechanics extends far beyond the laboratory. It has reshaped our understanding of nature, challenged our assumptions about the universe, and opened up new possibilities for technological innovation. The deep implications of quantum mechanics went beyond just altering the way scientists view particles and energy. They fundamentally changed how we understood the very fabric of reality. As quantum mechanics took root in the scientific community, the questions it raised became more profound. If the universe at the subatomic level is inherently probabilistic, what did that mean for our macroscopic world, our sense of free will, and even our understanding of causality? The philosophical and practical challenges posed by quantum mechanics continue to shape modern science, and they challenge our deepest assumptions about the nature of existence itself. Perhaps the most unsettling consequence of quantum mechanics was the idea that act of observation plays a central role in determining the state of a system. The collapse of the wave function upon measurement suggested that reality itself, at least at the quantum level, did not exist in a definite state until it was observed. This notion of observer-dependent reality was at odds with the classical view that the universe existed independently of human observation. In classical physics, reality was objective and could be described entirely by the laws of nature, independent of whether anyone was there to observe it. But in quantum mechanics, the observer seemed to influence the very outcome of the experiment. This is known as the measurement problem, a conundrum that remains one of the most perplexing aspects of quantum theory. The measurement problem raises serious questions about the role of consciousness in shaping reality. Could it be that the mind itself, through the act of observation, somehow determines the course of events? This notion touches upon deep philosophical issues, such as whether consciousness is central to the structure of reality, and it leads to questions about the nature of free will. If the universe is probabilistic, governed by quantum uncertainties, then the deterministic framework that underpins our everyday experiences no longer holds. The traditional notion that every action has a cause becomes murky in a world where causality is replaced by probabilities. Is the future, therefore, determined by the present, or is it a realm of infinite possibilities, where outcomes are never certain? One of the most intriguing implications of the probabilistic nature of quantum mechanics was its impact on the nature of time itself. In classical physics, time was a linear, irreversible flow, an absolute entity that moved in one direction. But the probabilistic framework of quantum mechanics suggested that time, at the most fundamental level, may not be as straightforward as once thought. The uncertainty inherent in quantum processes opened up the possibility that time itself could be more fluid, more interconnected with the conditions of the quantum system than previously believed. This shift led to the exploration of quantum theories of gravity, and the idea that time could be understood not as a rigid backdrop against which events unfold, but as something deeply tied to the behavior of quantum fields and particles. As quantum mechanics continued to evolve, it became clear that the traditional view of space and time as separate, absolute entities was no longer sufficient to describe the complexities of the quantum world. Quantum field theory, which views particles as excitations in fields that permeate space and time, led to a new understanding of the relationship between space and time. In this view, the fabric of space-time is not a passive stage on which events occur, but an active participant in the creation and behavior of particles. This notion, while still deeply theoretical, has influenced modern theories of quantum gravity, string theory, and the search for a unified theory of the fundamental forces of nature. The uncertainty and probabilistic nature of quantum mechanics also challenged our understanding of determinism. In classical physics, determinism was a fundamental principle. Given the initial conditions of a system, the future behavior of the system could be predicted with absolute certainty. But quantum mechanics introduced a new understanding of nature, one where outcomes could only be predicted probabilistically. This was not just a limitation of measurement, it was a fundamental feature of nature itself. The idea that the future could not be predicted with certainty, but only in terms of probabilities, appended centuries of scientific and philosophical thinking. This shift to probabilistic thinking was most famously encapsulated in the works of Werner Heisenberg, who formulated the uncertainty principle in 1927. Heisenberg's principle stated that certain pairs of properties, such as a particle's position and momentum, cannot both be precisely measured at the same time. This was not due to technological limitations, but rather an inherent property of quantum systems. The uncertainty principle thus introduced a fundamental limit to the precision with which we could know the state of a system. The more accurately we measured one property, the less accurately we could know the other. This limit on knowledge challenged the idea that the universe could be fully understood through the lens of classical determinism. While many in the scientific community initially resisted the probabilistic nature of quantum mechanics, gradually became accepted as the most accurate description of the physical world at the subatomic level. The success of quantum theory in explaining phenomena such as atomic spectra, the behavior of semiconductors, and the interactions of particles in high-energy physics experiments provided compelling evidence for its validity. Quantum mechanics not only explained existing experimental data but also led to new technological advancements, such as the development of lasers, transistors, and medical imaging techniques. However, despite its successes, quantum mechanics has continued to spark debate. One of the key issues that remain unresolved is the interpretation of quantum mechanics itself. The Copenhagen interpretation, proposed by Niels Bohr and Werner Heisenberg, suggests that the wave function of a quantum system represents a probability distribution of possible outcomes, and that the act of measurement causes the wave function to collapse into a definite state. This interpretation, while widely accepted, has been criticized for its reliance on the idea of wave function collapse and the role of the observer in determining reality. An alternative interpretation, known as the many worlds interpretation, was proposed by Hugh Everett in 1957. According to the many worlds theory, every possible outcome of a quantum event occurs, but in separate, non-interacting parallel universes. In this interpretation, the wave function does not collapse upon measurement. Instead, the universe splits into different branches, each corresponding to a different outcome. The many worlds interpretation eliminates the need for wave function collapse, but it raises its own set of questions, such as how to interpret the concept of parallel universes and whether it implies that all possible outcomes, no matter how improbable, are realized. Another interpretation, called the pilot wave theory or de Broglie-Bohm theory, proposes that particles always have definite positions and velocities, even when they are not being observed. In this view, quantum mechanics still operates with a deterministic framework, but the particles are guided by a hidden, non-local wave function. The pilot wave theory avoids the issues of wave function collapse and observer dependence but introduces new complexities, particularly regarding the non-local nature of the theory. The philosophical implications of these different interpretations have been hotly debated for decades. Each interpretation offers a different view of reality, and each raises questions about the nature of the universe and our place within it. For instance, if the many worlds interpretation is correct, it suggests that every decision, no matter how small, leads to the creation of a new parallel universe. Does this mean that there are infinite versions of us, each experiencing a different outcome to every decision? And if so, how should we understand our role in this vast multiverse? Despite the ongoing debates over the interpretation of quantum mechanics, there is no doubt that the discovery of uncertainty and the probabilistic nature of quantum systems has had a profound impact on science and philosophy. It has changed the way we think about the universe, introducing a new level of complexity and mystery to the natural world. It has also opened up new possibilities for technological innovation, from quantum computers to advanced medical imaging techniques, all of which rely on the principles of quantum mechanics. The physics discovery that destroyed certainty has reshaped our understanding of the world at its most fundamental level. It has forced us to embrace uncertainty, to acknowledge the limits of our knowledge, and to reconsider the very nature of reality itself. As we continue to explore the implications of quantum theory, we may find that the universe is even stranger and more mysterious than we ever imagined, and that the discovery of uncertainty was just the beginning of a new era in scientific exploration. The rise of quantum mechanics marked a profound shift in the way scientists viewed the nature of reality. Among the most significant aspects of quantum theory was the discovery that particles could exist in multiple states at once, a concept that seemed to defy all traditional logic. This phenomenon, known as superposition, suggested that particles were not confined to one specific state or position until observed. Instead, they existed in a superposition of multiple states, each with its own probability. This idea was completely alien to the deterministic worldview of classical physics, where objects were assumed to have fixed, predictable positions and properties. Classical mechanics, grounded in the work of Isaac Newton, had operated on the assumption that if you knew the initial condition of a system, such as the position and velocity of a particle, you could predict its future state with perfect accuracy. However, quantum mechanics upended this certainty by showing that at the quantum level, the future was not deterministic but probabilistic. This meant that the future of a quantum system could only be described in terms of the probability of its possible outcomes. The most famous experiment that illustrated the principle of superposition was the double-slit experiment. When electrons were fired at a screen with two slits, they produced an interference pattern, much like waves of light would. This suggested that the electrons were behaving as waves passing through both slits simultaneously. However, when the electrons were observed, they behaved as particles passing through only one slit. The key takeaway from this experiment was that the act of observation forced the electron to choose a specific state, collapsing the superposition and determining their position. This strange behavior of particles led to a fundamental shift in our understanding of reality. Quantum mechanics revealed that at the smallest scales of nature, the act of observation played a crucial role in determining the outcome of events. This was a radical departure from classical physics, where objects were thought to exist with well-defined properties, independent of human observation. In quantum theory, reality itself seemed to depend on the observer, challenging the idea of an objective universe that existed outside of our perception. The consequences of this discovery were far-reaching, both scientifically and philosophically. If particles could exist in multiple states until observed, what did that say about the nature of reality? Was the universe truly objective, or was it shaped by the act of observation? These questions challenged not only the foundations of physics, but also the very essence of human experience. The uncertainty that quantum mechanics introduced into the fabric of reality forced scientists, philosophers to confront deep questions about the nature of knowledge, perception, and existence. Quantum mechanics also introduced the concept of entanglement, another phenomenon that defied classical understanding. In entanglement, two particles could become linked in such a way that their states were interdependent, regardless of the distance between them. If one particle was measured, the other particle's state would instantly be determined, even if it was light years away. This non-local behavior seemed to challenge the classical idea that objects had independent property, and it suggested that the universe was more interconnected than previously imagined. This strange, interconnected world of quantum mechanics has led to groundbreaking advances in technology, from lasers to computers to medical imaging. Despite its unsettling implications, quantum mechanics has become the foundation of much of modern science and technology. The discovery of uncertainty in the quantum realm destroyed the certainty that classical physics had promised, but it also opened the door to a new understanding of the universe, one that embraces the strange, unpredictable, and probabilistic nature of reality. One of the most profound revelations of quantum mechanics was the concept of entanglement, a phenomenon that defied classical intuition and fundamentally altered the way we understood the universe. Quantum entanglement occurs when two particles become so deeply linked that the state of one particle is directly correlated with the state of the other, regardless of the distance between them. This means that when one particle is measured or altered, the other particle's state is instantly determined, even if it is light years away. This seemingly instantaneous transfer of information and across vast distances, faster than the speed of light, challenged the very foundations of relativity, which stated that no information could travel faster than light. Entanglement was first described by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935 in what became known as the EPR paradox. Einstein referred to this phenomenon as spooky action at a distance, as it seemed to imply a connection between particles that was not bound by the limitations of space and time. The EPR paradox posed a challenge to the completeness of quantum mechanics, suggesting that there might be hidden variables yet to be discovered that could explain the seemingly non-local correlations between entangled particles. Despite Einstein's skepticism, subsequent experiments, most notably those conducted by John Bell in the 1960s, confirmed the reality of quantum entanglement. Bell's theorem showed that no local hidden variables could account for the strange correlations observed between entangled particles. This was a crucial moment in the history of physics, as it not only validated quantum mechanics but also forced scientists to accept that the universe operated in ways that were completely at odds with classical ideas of causality and locality. The implications of quantum entanglement extend far beyond theoretical physics. In recent decades, entanglement has become a cornerstone of emerging technologies like quantum computing and quantum cryptography. Quantum computers, which harness the power of entangled particles to perform calculations, promise to revolutionize computing by solving complex problems that are currently beyond the capabilities of classical computers. Entanglement also plays a key role in quantum cryptography, where entangled particles are used to create unbreakable codes for secure communication. These developments have made entanglement not only a central concept in theoretical physics but also a practical tool for cutting-edge technologies. However, entanglement also raises deep philosophical questions about the nature of reality and the role of observation in shaping it. If particles are entangled, and their properties are determined instantaneously upon measurement, what does this say about the fabric of space and time? Classical physics viewed space and time as distinct, separate entities that existed independently of the objects within them. But quantum mechanics, through the concept of entanglement, suggested a more interconnected universe where particles could be linked across space and time in ways that defied the classical understanding of separateness. Moreover, entanglement challenges the very notion of causality. In classical physics, every effect has a direct cause, and this chain of cause and effect determines the future behavior of a system. But in the quantum world, the behavior of entangled particles appears to be non-local, meaning that their states are determined not by a local cause, but by a broader, global connection. This raises questions about the nature of causality at the quantum level. If particles are interconnected in such a way that their states are instantaneously correlated, what does it mean for the concept of cause and effect in the quantum realm? The discovery of quantum entanglement and its subsequent experimental confirmation was a game changer for science. It not only validated the strange, counterintuitive predictions of quantum mechanics but also forced physicists to rethink some of the most fundamental assumptions about how the universe works. The concept of entanglement destroyed the certainty that classical physics had long provided and opened up a new realm of possibilities where the boundaries of space, time, and causality were not as fixed as previously thought. As quantum mechanics continues to shape modern technology and deepen our understanding of the universe, the study of entanglement remains a key area of research. The realization that particles can be connected in ways that transcend classical concepts of space and time has had profound implications for fields as diverse as computing, communication, and cosmology. Quantum entanglement is not just a theoretical curiosity. It is a vital part of the scientific and technological landscape, offering insights into the nature of reality and the potential for future breakthroughs in quantum technologies. The realization that the universe behaves in probabilistic ways at the quantum level where certainty no longer holds led to one of the most profound shifts in the history of science. One of the critical elements of this discovery was the development of quantum superposition, which introduced the idea that particles, such as electrons, could exist in multiple states at once. This phenomenon shattered the classical notion that objects have well-defined, predictable properties. In the classical worldview, an object, such as a coin, when tossed, could be seen as either heads or tails, but quantum mechanics proposed that until observed, the coin was in a state of superposition existing as both heads and tails at the same time. The principle of superposition was first articulated in the early 20th century, most notably by Erwin Schrödinger, who mathematically formalized it through his famous wave equation. This equation described how particles could be in a superposition of different states, and the act of measurement would cause these possibilities to collapse into one defined state. Schrödinger's famous thought experiment involving a cat placed in a box with a radioactive atom was designed to illustrate the bizarre implications of quantum superposition. According to Schrödinger, until the box was opened and the cat observed, the cat would exist in a superposition of being both alive and dead. This paradox was used to highlight the strange, counterintuitive nature of quantum mechanics. Superposition became one of the core principles of quantum mechanics, fundamentally altering our understanding of the nature of reality. Before this discovery, it was assumed that the state of an object or particle was definite and that it existed in one well-defined state at any given moment. In classical physics, this was a given. Objects had a specific position, velocity, and momentum, and these properties could be measured accurately at any time. However, quantum mechanics revealed that at the microscopic level, particles do not exist in a definite state. Until observed, they exist in a superposition of all possible states, each with a certain probability. The act of observation was thus critical in determining the outcome, forcing the wave function, which describes the probability of various states, to collapse into a single reality. This shift from certainty to probability raised profound questions about the nature of reality itself. Classical physics had offered a deterministic universe, one where if we knew the present conditions, we could predict the future with certainty. Yet quantum mechanics suggested that the universe at the quantum level was inherently uncertain, and the future could only be described in terms of probabilities. This idea was unsettling because it fundamentally challenged the deterministic worldview that had dominated physics for centuries. It meant that at the quantum level, we could no longer rely on precise prediction of future events. Instead, we had to deal with probabilities and uncertainties. As quantum mechanics continued to evolve, the implications of superposition became even more profound. One of the most striking developments was the realization that superposition was not limited to individual particles, but extended to larger systems as well. The concept of quantum coherence, in which different parts of a system can remain in superposition, led to the development of quantum computing. In a quantum computer, qubits, quantum bits, can exist in a superposition of both 0 and 1 states at the same time. This ability to process information in multiple states simultaneously enables quantum computers to solve certain problems much faster than classical computers. The superposition of states, which had initially seemed like a theoretical oddity, had become a practical tool for developing technologies that were poised to revolutionize industries. However, superposition also raised difficult questions about the role of the observer. If particles can exist in a superposition of states, how does one explain the fact that we observe definite outcomes in the macroscopic world? This was a central challenge for physicists. In the world we experience, objects appear to have clear, measurable properties. A cup of coffee, for example, does not exist in a state of superposition, behaving as both full and empty at the same time. Yet quantum mechanics suggests that at a deeper level, everything is governed by probabilities, and it is only through observation that a definite state emerges. This tension between the quantum world, where uncertainty reigns, and the classical world, where objects appear definite and predictable, lies at the heart of the measurement problem in quantum mechanics. The notion that observation affects the outcome of quantum experiments led to debates among physicists about the role of consciousness in shaping reality. Some, like Niels Bohr, argued that the wave function collapsed upon measurement, and this collapse was an inherent feature of nature. Others, like Eugene Wigner, suggested that consciousness itself played a central role in the collapse, implying that human observation was crucial to determining the state of a quantum system. While these debates continue, the discovery of superposition and the realization that quantum systems can exist in multiple states simultaneously forced us to confront the limits of our understanding of reality and the nature of measurement. The introduction of quantum superposition also had profound implications for the philosophical foundations of science. The idea that particles could exist in multiple states simultaneously blurred the lines between what was real and what was possible. If reality could be in a state of superposition, then what did that say about the nature of reality itself? Could the universe be governed by laws that allowed for multiple realities to coexist? These questions have yet to be fully answered, but they continue to inspire deep philosophical inquiry into the nature of existence. As we continue to explore the implications of quantum mechanics, superposition remains one of its most perplexing and fascinating aspects. It not only challenges our classical understanding of the world, but also opens up new possibilities for technological advancements. Quantum computing, quantum cryptography, and quantum sensors, all of which rely on the principles of superposition, are set to transform the future of technology. Despite its strange and counterintuitive nature, superposition has become a cornerstone of modern physics and is one of the key ideas that has shaped the new understanding of the universe. The discovery of superposition destroyed the certainty of classical physics and opened up a new era of scientific exploration, where uncertainty and probability reign at the heart of reality. One of the most significant and perplexing aspects of quantum mechanics is the uncertainty principle, introduced by Werner Heisenberg in 1927. This principle fundamentally altered our understanding of the universe by establishing a limit to how precisely we could measure certain pairs of properties, such as position and momentum, of a particle. The more precisely one of these properties is measured, the less precisely the other can be determined. This relationship was not due to limitations in measurement tools, but rather an intrinsic feature of nature itself. Heisenberg's uncertainty principle suggested that uncertainty and indeterminacy are not anomalies or failures of measurement, but essential characteristics of the quantum world. At the heart of the uncertainty principle was the realization that, in the quantum realm, the act of observation itself could disturb the system being measured. This was a profound departure from classical physics, where it was assumed that the act of measuring a property, such as the position of a ball or the speed of a car, did not fundamentally alter that property. In quantum mechanics, however, the process of observing or measuring a particle at a specific moment in time could cause a disturbance that made it impossible to know other properties of the particle with certainty. This realization shattered the classical notion of determinism, where knowing the present state of a system allowed us to predict its future with absolute precision. The uncertainty principle has profound philosophical implications as well. It challenges the classical worldview, which was based on the belief that the universe was a predictable machine governed by fixed laws. In this classical view, if we had complete information about the state of a system, we could predict the future with certainty. However, Heisenberg's uncertainty principle introduced an inherent unpredictability into the fabric of reality, where even if we could know everything about a system at one moment in time, we could not determine its future state with precision. This undermined the deterministic outlook that had dominated scientific thought since the time of Isaac Newton. Heisenberg's principle also raised important questions about the nature of reality itself. If the properties of particles were subject to uncertainty, could the entire universe be understood in probabilistic terms? Did this mean that all physical processes, from the motion of planets to the behavior of subatomic particles, were inherently unpredictable? In classical physics, the universe was imagined as a giant clockwork mechanism where each part interacted in a well-defined and predictable manner. But the uncertainty principle suggested that at the most fundamental level, the universe was not a deterministic machine but a probabilistic one, where outcomes could only be described in terms of likelihoods. One of the most striking consequences of the uncertainty principle was the redefinition of the concept of causality. In classical physics, causality was seen as a straightforward concept. Every effect had a cause, and given the initial conditions of a system, its future state could be determined. But in quantum mechanics, the future of a system could not be predicted with certainty. The probabilistic nature of quantum mechanics meant that even if we knew all the present conditions of a system, we could not determine exactly how it would evolve over time. Instead, we could only calculate the probabilities of various possible outcomes. This shift from certainty to probability marked a dramatic departure from classical idea of causality and had far-reaching implications for our understanding of the universe. The uncertainty principle also challenged the traditional view of space and time. In classical physics, it was assumed that space and time were absolute and objective framework in which events occurred. However, the uncertainty principle suggested that the very act of measuring a particle position or momentum involved a limit to our knowledge of space and time. This raised important questions about the nature of time itself. If the position and momentum of particles could not be precisely determined at the same time, what did that mean for the flow of time in the macroscopic world? Was time itself subject to uncertainty, or was it only the quantum realm that exhibited this behavior? Despite the philosophical challenges posed by the uncertainty principle, it has been experimental, confirmed countless times, and remains one of the cornerstones of quantum mechanics. The uncertainty principle has been crucial in explaining phenomena such as the behavior of electrons in atoms, the interaction of light with matter, and the behavior of particles in high-energy physics experiments. In fact, the uncertainty principle is essential to understanding why atoms do not collapse under their own electromagnetic forces. The uncertainty in the position and momentum of electrons within an atom ensures that they do not spiral into the nucleus, as classical physics would have predicted. The uncertainty principle has also had practical implications for technology. It has played a crucial role in the development of technologies such as quantum computing and quantum cryptography. In quantum computing, for instance, the uncertainty principle allows qubits quantum bits to exist in a superposition of states, enabling them to perform calculations much faster than classical bits. In quantum cryptography, the uncertainty principle ensures the security of communication, as any attempt to eavesdrop on a quantum communication would disturb the system and alert the parties involved. The discovery of the uncertainty principle was one of the key moments in the physics revolution that destroyed the certainty of classical mechanics and replaced it with the probabilistic nature of quantum theory. It forced scientists to rethink their approach to understanding the universe, introducing a level of indeterminacy that had not been considered in the classical worldview. The uncertainty principle not only reshaped the field of physics but also had far-reaching implications for philosophy, technology, and our fundamental understanding of reality. In a world where uncertainty reigns, the universe is no longer a predictable machine, but a place where probability and possibility define the future.